So here's an idealized system we can now rationalize. It's going to happen where I have a mass flow rate going in, or just a mass flow rate of the system. There's a pressure here, right? And then we have some back pressure in your test device. So the lower and lower I make this pressure, and then the lower and lower I make this pressure, the more I'm going to have to suck this mass through this section right here. So the lower I go, ideally, you would just keep speeding things up. Okay, so this is the throat. And there's an exit. And then let's say you measured pressure through all these parts right here, right? Just use your Venturi tube to actually measure the pressures. And they did this back in the day, which is impressive to me. They just measure the pressure at every what. So you take a Venturi tube over here, and you can actually just create a plot of how the pressure behaves in something like here. Okay, when you do that experiment now, you get this classic concept, right? I think I have, here's like a pressure. Here's that P star over P naught is a critical condition. Here's, this is one. I think I drew it better in the notes. This is just one. And then if the back pressure is equal to this pressure here, well, there's no flow. The pressure is just constant throughout all of it. Okay, all I need to have here is xt. Xt will be the throat section. So what's happening right here is what's interesting. So, right, as I keep decreasing and decreasing, right, so here's like a back pressure 1, 2, 3. So this is decreasing back pressure. Goes down, down, down. Eventually what happens is this situation where before it was all smooth, but once you hit this part right here, when Mach went critical, once I decreased the back pressure enough that the flow velocity here became the speed of sound itself, if I'm surpassing that, then what happens, right, as you move along here, is that the pressure has to discontinuously adjust to become this back pressure. It doesn't smoothly do it, and that's due to the mass flow rate and this idea of a Mach number. We'll talk more, I think, about like why on earth do you get this discontinuous change when we talk about a shock wave. But that's later, because I don't see a reason to really talk about it right now, only because, right, it's the idea of transitioning from Mach less than 1 to Mach 1 to Mach past 1. If you get past Mach 1, it doesn't matter what you do. You're just limited right here at this stage. And then past there, you'll get this change. So if you're at Mach 1, you're limited on what you can do on that throat section. And that goes down to that critical mass flow rate, right? We could calculate that just based on the properties of the gas itself. So this mass flow rate diagram, how much mass of the gas can actually shove through this throat right here, right? Here, let's say this is back pressure. This is the back pressure axis. Okay, so right here we'll have the back pressure equaling this pressure right here, so there's no flow rate, right? Once this back pressure is equal there, it goes by reduce, 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 reduce. So going here, this is order of decreasing. So I'm decreasing the back pressure, right? What happens is you level off, right? So decrease, 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 but then after a while, and here we'll say this is right here, right? When it becomes flat, that's the Mach 1. So right when my back pressure got so low enough that that I got to P star over P naught being 1, you level off on mass flow rate. You're limited. And that's just what you have to deal with when it comes to these compressible throat problems. Is it doesn't matter what you can achieve in the back pressure to speed up the mass flow rate. You can't get any more mass flow rate because you're limited by the throat. You just hit a wall. or past there the pressure could get lower, but you just cannot get further than that. And I think that's interesting. And that makes sense to us because after relationships, we figured out that if we found a Mach at 1, we just had this number of mass flow rate that couldn't change. It's based on stagnation properties. Okay, so the second situation is convergent divergent nozzles, which is really the same, only the really difference that happens. So here's your throat. Right, is now, before this was all scrunched up to just be a line. Right, the divergent part is you're now taking the throat, and instead of having it discontinuously just become open, right, you now have this slow divergent section. So really what you did, right, in the previous case, right at x equals t, right, what happened? Right, so for just the convergent nozzle with an exit part, you eventually got to this point where the dA dx blew up to infinity. But with a convergent divergent nozzle, right, now you have that the dA is finite. It slowly expands. So something different is going to happen. Okay. Same graph. You just measure your venturi pressure along each little thing, make a discrete plot, connect the lines. Okay. Same thing. If they're equal, there's no flow rate. And then here's xt, here's the depth of throat. Like this. Like this. So now, again, I have decreasing back pressures. Decreasing back pressures. So there's a P. Back pressure right here. Lowering this pressure more and more and more and more and more to try to increase the velocity that's happening through this duct right here. So this goes down, down, down. And then at Mach, you get a corner, which is people were impressed with that you just find a corner like this. It really looks like a corner too if you see it. And eventually, when you surpass, so this corner one right here, this is going to be Mach equaling 1. So Mach equal 1, you have this corner where you can still get back to your back pressure, but you had this sharp corner that occurred right here. And now right here, this is what goes weird. This is now supersonic flow through a convergent divergent nozzle. And that's the impressive, amazing part about this, is because you got to Mach past 1, right? Sped up, sped up, sped up. And then if this was Mach 1 now faster, I'm restricted to being Mach 1 here. But then when I get out to here, and Mach is past 1, well, now everything starts going faster because of those relationships we had. Remember, it inverts in your head of what happens when you go supersonic flow. So now what happens is when this flow reaches there, it gets more and bigger and bigger and bigger and bigger, which is problematic as well. But not problematic, it's really great. It just, you get this extremely drop in pressure and get more accelerating flow outwards. So that's really the isentropic relationships, how to really rationalize these things. Mechanically, what you use those equations for are really just problems like that, though. And there's an infinite number of them where you have sort of a stagnation type of problem like this, and you have a state B and a stagnation state A, or something like this. This is Mach 1. Then you're trying to figure out states, like let's say a downstream state or an upstream state. And you use those state equations to make predictions based on this stuff. So like, what's the mass flow rate out here? Well, I can go from stagnation to state B, and I can talk about pressures, and I can talk about densities. You can get there. You can what the density would be there, and what the Mach would be there. You could solve for these. It's an infinite number of examples, but I haven't assigned any of them, but hopefully you understand maybe some of them are. I might post some example problems, but since this is all concept-driven compressible flow stuff, maybe I'll just end there. So those are the isentropic flow relationships that we had. There were a lot of those equations, right? But maybe you can just digest them and just see that it's just relating state A to state B, just like you did with compressible flow, where I try to get liquid from A to B. Now you're getting gas from A to B. You're just using fancier equations. And in fact, you don't even use these equations. Usually there are just these tables you would look up or graphs you would plot. And you could just like, drag your finger and go like, okay, so this ratio would be this number in sulfur or something. So maybe it's not as scary as some people make it out to be.